Okay.
Our own Jorge, please tell us about distinguishing entangled sets.
Okay, yes. So the the topic here is, well, just entangled sets. Remember, this has to do with Van Gardner's action. Van Gardner proved that under PFA, any two Aleph one dense sets of reals can be isomorphic. And then it was later proved using these objects called increasing sets and entangled sets, that the consistency of the negation of that fact is also true, right? So let me put the definition. First, the type. So let A and B two subsets of the real numbers of the same cardinality. We say that the type of AB is tau, where tau is a function from n into 2 if for any I in n, AI is less than BI, if and only if tau of I equals 0. And here AI and BI is the ith element of A and B with respect to its increasing order. Analogously, if A and B are subsets of R to the n, then type of AB is tau if and only if type of all of its pairs is tau. Tau for each A in A and B in B.
So the first thing, this really is like some kind of monotheoretic type, even though you're only recording things about AI and BI together, transitivity tells you all of the other relations. Is that right?
Not necessarily, but
There's some independence where
yes, like in general, you do not know what it will be the relation between AI and BJ, for example. The idea here is that when we work with entangled sets, we will always have like the following drawing. Let first me define entangled sets. So the definition, E subset of the reals is, let's say, kappa and entangled. If and only if for every family A of subsets of E of size n, and let me put it like this: family of size kappa, family of pairwise disjoint sets, and for every tau in 2 to the n, there are A and B in A such that tau, or the type of AB, is tau, right? An n-entangled set is simply an omega 1 n-entangled set. So omega 1 n-entangled is called entangled. And entangled is, sorry, this is n-entangled. And entangled is n-entangled for every. So the idea here is that by, well, using the second countability of the reals, if you can have a pair of elements which look like this, then you can always refine your families such that you can find here some intervals that are ordered in this way, in such way that A0 and B0 are here, A1 and B1 are here, A2 and B2 are here. So in this way, like the picture of A and B can always be thought as a nice picture. And yes, just to complete the drawing, let's say that the type is 0, 0, 1, 0. Then in this case, we will have here A0, B0, A1, B1, well, B1, B1, A1, right, yeah, two, and A3, B3, right? Great. So it is a theorem of Abraham, Rubin, and Shelah, that it is consistent that for every n in the natural numbers, there is an n-entangled set but there are no entangled sets. No, for every n, there is one, but there are no one which is n-entangled for every n.
Okay, I thought that was, and there's a sub, just n entangled, not n plus one.
Exactly.
I'm sure they prove that as well.
That's the thing, and that's why I want to present this today, because for some strange reason, the consistency of entangled set was known since their paper. The consistency of n entangled sets for each n, but no complete entangled sets was known. But somehow no one even asked whether it was consistent, whether n entangled sets might exist and no n plus one entangled sets may exist. So in a recent paper, Haroy, Levin, and Notaro proved that under covering of meager equal C, there is for each n in the natural numbers an n entangled set sorry, not an n entangled set, but a C
Okay,
n
that makes sense.
entangled set, which is not Cn plus one. And then in that same paper, they proved that for under the same conditions, there is an n-entangled set. Sorry, there is an entangled set. See, there's a C entangled set. Sorry. When I say C entangled set, is Cn entangled set for every n, which is homeomorphic to a subset, which is not even. C to entangled. So entangledness is not a topological property in the case of Cn entangled sets. Of course, their theorem is in particular true, for example, under CH, in which what they conclude is that there is just an entangled set with those properties, right? In that same paper, they ask 3 questions, one of which I will address today. Roy, Levin, Sarah. Fix. And in the natural numbers, is there an n-entangled set? But no n plus 1 entangled sets. And this is a sentence consistent.
Size maybe one.
Yes, here of size omega 1. Mhm. They also ask 2 other questions. One of which is, okay, the definition of entangledness makes sense for every total order, not just over the real numbers. Esteban noted this. He also noted that in case of 3 entangled, as a total order is 3 entangled, implies that that total order is separable. So for 3 entangled sets, there are only on the real numbers. For 2 entangled sets, 2 entangledness implies that the total order is CCC. So it makes sense to talk about 2 entangled Suslin lines, right? Another problem which I will not talk about today because I do not have an answer yet, but it's worth mentioning of them, is whether it is consistent that there is a 2 entangled Suslin line, but not entangled sets of the reals. That there exists as Suslin 2 entangled. But no 2 entangled sets reals.
Can I ask, so I guess not every Suslin line is too entangled, right?
No, not necessarily.
But there are some, right? Consistently, you can.
Yes, consistently there are some. They construct one using a diamond in their paper, and before that, I think it was Kruger who constructed one using forcing.
Mhm.
I haven't looked the paper quite carefully, but I believe it's basically Cohen.
What if you have like a genius system, like entangled?
No, I don't think that there's that whether that implication is known or not. What they do in
Homogeneous means that they need to subordinate isomorphic. Isomorphism should
Well,
kill
no, I think
entangled.
it only in the sense of
use-
if you have PFA of S, PFA
Uh-huh.
preserve,
uh,
preserves, which has proper.
Right.
the-
Then you get to the-
You're just like
Okay, yeah. okay.
But
So-
if it is, then no, right? Because you have two just the isograph of the isomorphism is going to kill two entanglements.
well, there's the answer.
Right, so that's
Actually, what they use in order to construct this Suslin two entangled line is basically like a free Suslin tree, which is like the opposite. So well, now let me just talk about the theorems that I proved today. There's a kind of well, the first theorem, I have already speak about this action, FCA delta, which is you have construction schemes. You can talk about a notion that is called delta capturing. This notion of delta capturing is implied by the continuum hypothesis, and will also, for example, holds in the Cohen model. And under FCA, we can in some way improve this theorem here. So there is a collection let's say n in the natural numbers of entangled of sets of reals such that one for every n in the natural numbers, n is n entangled, not n plus one, and two, all of them are pairwise isomorphic. Sorry, pairwise isometric. Here I'm talking, of course, not the entangled sets are not constructed actually over the real numbers, but over the Cantor space with the usual metric, right? So this is not a theorem strictly about the reals, but about the Cantor. If you talk about the reals, you should put just here homeomorphic, pairwise homeomorphic. And there's one extra entangled set here, which is fully entangled. So yes, this proof, I believe it's, I mean, it's a good proof because the idea is that with this action, basically all what you need to do is to make your construction in order to guarantee that the set En is entangled, and the construction scheme will make your set not n plus one entangled. So one advantage of constructing things using construction schemes in comparison with recursion is that with recursion, nothing is for free, right? If you want to have an extra property, like you will have to modify your recursion. With construction schemes, usually like you make a construction and you can analyze under that construction whether certain properties hold or not. And is the case of this thing here. The next theorem is, well, a solution to that problem. This. In order to formalize this solution, we need to talk a little bit about something which Emily talked one of last year. Emily speak about the parameterized versions of PFA. So we also have a version of parameterized versions of PFA together with Osvaldo and Esteban. One of those parameterized versions, which I do not know whether it coincides with one of Emily or not, but it would be the proper forcing action restricted to n-entangled sets, particularly to one n-entangled set. So this proper forcing action tells you that PFA is true for all proper forcings which preserve the n-entangledness of E. So the theorem should be that PFA n and E implies that there are no n+1 entangled sets. And well, if you want to generalize a little bit a theorem of Osvaldo and Esteban, the proofs are really the same, so I do not attribute them to me. But under this same action, you can already prove that MA holds and that the p-ideal dichotomy holds. So these
But
are,
Sorry, but OCA probably fails, right?
yes,
because of-
OCA will fail because there exists an entangled
okay.
set. Now, this also has to do with the proof.
So, so the subscript on the PFA just indicates that E is n-entangled.
Exactly. Actually, just maybe it's a good idea to put this theorem in its most general form because it might be useful for some. The whole idea behind this theorem is the fact that independent sets of graphs are preserved well under proper forcings via Niemann iterations. So for example, with Suslin trees, we have an iteration theorem for countable support iteration, which tells you if a countable support iteration, if each member of a countable support iteration preserve Suslin trees, then the full iteration will preserve a Suslin tree. In order to prove that theorem, it seems like it's very necessary to use the Suslinness of a tree, or well, the fact that the tree is a partially ordered set. Trying to prove those kinds of preservation theorems for graphs without uncountable independent sets is usually a little bit more difficult with countable iteration support of proper forcings. This problem disappears almost completely when you use Niemann iterations. So for Niemann iterations, the theorem is basically the following, and from this theorem, you can deduce that PFA. So the theorem, it will probably appear in a joint work with Osvaldo and Esteban, but the ideas of that theorem already appear in the paper of Esteban Osvaldo of entangled sets. So let me just attribute them to them. Usman and Todorchevich, although the ideas. But the idea is the following. Let's say A be a family of uncountable graphs. And I shouldn't say uncountable because I will say over omega 1 without uncountable independent sets. There is a proper forcing P such that P forces PFA of A, where PFA of A is PFA for all proper forcings with which preserve that each graph in A doesn't have uncountable independencies. Does this make sense? So note that being n-entangled is a property which can be characterized by a finite number of graphs without uncountable independent sets, namely the graphs that are telling you that the type is not tau.
Sorry, what are you claiming?
That if you have an n-entangled set,
Yes.
then you can define for each set of the real numbers, you can define the graph, let's say G sub tau, whose vertices are the elements of the set and whose edges are the pair of vertices whose type is not tau. And a set is n-entangled if and only if none of those graphs have a. Yes.
Okay, but that's a definable family. So here you want to have a definition, because when you add reals, you're adding usage. Oh, no, you're just looking at those actual sets.
Uh-huh.
Okay.
Yes.
So when you add, even if you add reals,
Yes, they doesn't matter.
But vertices are n tuples. I think you said singletons, but you meant n tuples.
Yes, n tuples. Sorry, n tuples.
So just to make sure that I'm
Yes.
not
No,
completely
you're right. And well, of course, you have to give change a little bit the definition of type so that you can actually consider n
Oh,
tuples
okay,
which
okay.
are not disjoint.
Yeah, you don't have
But
directed graphs.
there's really no problem.
But
That
can you
is,
prove this for directed graphs?
Huh?
Oh, no, sorry. No, never mind. I asked a stupid question.
Was that a stupid question?
Well, what does independent mean?
Ah.
It wasn't completely stupid, but you would have to make sense out of it.
okay, we're good now. If I start talking about construction schemes, then I will probably just give the definitions and that's it. So I will just talk about the other result and just announce the one on construction schemes, okay? Another way of looking, or well, one important thing regarding entangled sets is that the graph that I described previously of not having type tau is an open graph, right? The type defines an open graph, which means that there is a proper forcing destroying the n-entangledness of a set, right? It would be natural to use that proper forcing, that is the one from OCA, in order to kill the n+1 entangledness of a set while preserving the n-entangledness of a set. Unfortunately, that proper forcing might destroy the n-entangledness of a set. So this makes the problem, if it's not like very hard, at least not a completely trivial problem to deal.
Oh, sorry. You're saying that the theorem answers the first problem, is it?
Yes.
So you're saying that PFA n+1e implies that there's an entangled set?
Yes, the n-entangled set will be E.
Ah, so it's preserved.
Exactly.
I see.
For the other problem, I have to work maybe in some details. I don't say that I solve it because I haven't wrote those details, but the idea would be maybe basically to construct again a Suslin tree, which is to entangle, and in this case try to solve the problem in a similar way, but for PFA of the Suslin tree.
Yeah,
but
but Eurus whispered in my ear that he thought your proof was incorrect.
Oh.
It might be entangled. Because remember,
Oh,
it's
It
just,
depends on the definition of what it means for a Suslin tree to entangle. If it's the entire tree, yes, but I would imagine it means that a Suslin tree has a subset and entangled.
Well, just
No,
when I
everything
say
happens.
the Suslin tree, I'm
it's every uncountable subset is entangled,
No, well, the thing is that here we have to make a little bit, maybe I didn't make it, but there is a distinction between working with entangled Suslin trees and entangled Suslin lines. So here we're looking at the total order defined by the Suslin tree, and the Suslin line is two entangled if for every uncountable family of pairs of the thing, there will exist two which have
But
that
in the
type.
reals, you're talking subsets.
Uh-huh.
Not the reals.
Yes,
So it would make sense to talk about subsets of the Suslin line.
it makes sense to say that a subset of a Suslin line is,
That's if you're taking the whole line.
Yeah, no, I thought you said.
yes,
But if it's homogeneous, you have a function from here to here, and the pairs are A and
The reals are homogeneous.
No, but sets of reals are not.
I know,
And
that's
then
why
what-
I'm wondering about the definition. Is it a subset of the Suslin tree or is it the
Oh,
whole?
But
yeah.
subset.
No, it's the whole.
For the reals to be.
Not every
entangled
subset,
with
not every subset would be.
Yeah, but if your Suslin line is homogeneous, then this is right. So I'm just saying.
Yeah, the whole
homogeneous
Suslin line is not,
Suslin line.
the whole Suslin line is not to entangle.
Right.
Yeah.
But are you asking for the whole
Oh,
Suslin line to be to
okay, I
entangle or
see.
a subset?
Okay, so you want subset, huh?
Jorge,
Hmm?
are you asking for the whole Suslin line to be too entangled or?
oh, well, I'm asking for the existence of a Suslin line. If a subset of the Suslin line is two entangled, then there exists a Suslin line, right? A subset of a Suslin line is,
Subset, it's
Yes,
subset.
but that's not gonna have homogeneity.
Yeah,
Yeah,
exactly.
By
So-
definition, it's like-
So does PFA of S, you know, the PFA which preserves, does it apply, it doesn't apply to CA?
OC, no. No, yes,
No, no.
yes, yes, PFA of S,
Okay, so then if you could find one of these, then in PFA of S, it applies. to
Exactly.
CA, so there would be no entangled set.
exactly.
Okay.
The only problem here is that preserving the Suslinness of a line doesn't mean that you preserve the N and the two entangledness of the line, right? So that is that small thing that
That's a small thing. It's always a small, it's always a small thing.
Yeah.
yes, it's
Before you go away,
it's a small.
I didn't
Yes.
quite catch, so you said something about this requiring an even iteration. In
Exactly.
other words, so this does not work in a countable support iteration.
Uh,
It's clear.
For countable support, I do not know, but for many special cases of this theorem for countable support iteration is actually open problem in other papers. So yes, I think that basically is not known which kind of graphs can be preserved by countable support
But-
iteration.
So to get full, thing, you need for the families to be a large cardinality. Is that the problem for finite families?
No, not even for one graph. It's known for, yes.
Oh,
For the special case of Suslin trees, the graph defined by incomparability, there's a proof, but it's very special for, like, you cannot try to generalize that proof for more general graphs, like the fact that the Suslin tree is actually an order plays an important role in that. Okay. So definition, here we're fixing an entangled set E. So let E be an entangled set. This is the one that we want to put there. And let X be a subset of the real numbers, which is uncountable. This is the set that we want to destroy. It's n+1 entanglements. So fix kappa big cardinal. And let Sm of kappa be the collection of all elementary submodels of H of kappa, such that M is countable and all the objects of interest are in there. Xe and that's it. So the definition. Let M A be an element of Sm kappa to the n+1 times x to the n+1. So we say MA is a good pair if
So n is a sequence of n+1 elementary subblocks.
exactly.
No,
So,
PFA.
eh?
Usual PFA thing, I guess.
Well, the thing here is that not the usual, but like the second usual.
So that's the Niemann part, I guess.
Eh?
No.
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 So the thing is that when we want to construct a forcing with the elementary submodels, usually what we do is like we have sequences of elementary submodels and tuples.
Yeah.
But each elementary submodel is associated to one object.
Mhm.
Here, one single chain of elementary submodels will be one of the elements of interest. So what we will be interested in chains of elementary submodels. That is like the difference in this forcing.
Chains of n+1 chains.
Exactly.
So the n+1 doesn't go the other direction.
Exactly. That's the important part. So this thing is a good pair.
So the M itself doesn't need any structure.
The M?
Yeah.
Yes, I will say that
Oh,
yes. So this is a good pair. If one thing happens, M is n+1 many elementary submodels. So let me call its elements M0, M1, M2, right? So M equals M0, and let me just write it like this. Just by notation, Mn+1 is the universe. So this is a chain of elementary
So what
submodels.
is n+1?
Eh?
What is n?
The universe.
Universe.
Just by notation. So I can write the
Don't
second
want
point.
H kappa, you want all the way universe.
I just
I
want,
mean, that looks fine.
it's just a notation. Now it will be justified in the second point. So the second point is that for every I less or equal than n, AI is in mi+1 minus m. Right? So you have this usual sequence of elementary submodels. And what I'm saying is that A0 is here, A1 is here, A2 is here, and A3 is just outside the last node. That's what I put the universe. Huh? If you want.
But I thought it was in H kappa. No.
Yes, but all the elements are in X.
Everything would be in H cap.
Everything is in.
Okay.
That's why kappa is a big cardinal.
Big enough,
Big enough, not large.
but there is no dot in the bottom there.
Yes, there's no dot in the bottom, sorry. Right. So these are like the atoms of the forcing. And now the definition. Here is something which will appear as a question later. But like associated to the notion of an n-entangled set is the notion of an n-increasing set. A set is n-increasing if it is n-entangled, but just for one type, the type constant type 0 or the constant type 1. Which means that either all AIs are smaller than all BIs, or all BIs are smaller than all AIs. So what I will do is actually destroy the n+1 increasingness of the set. As a question, I have whether given a type tau, you can destroy the tau entangledness of that set. In the proof, you will know why it's yes, why increasingness is an important part. So definition, let P of X E be the family or the forcing of all the forcing of all finite families of wood pairs, of all P's finite families, finite collection of wood pairs such that one. This is just not a property, but a description of P, a notation. P is equal to M P0 A0 up to MP N sub P minus 1 ANP minus 1. So NP is the cardinality of P, and we index each pair in that way. And 2, for each I less than NP, we have that M0P A0I, this chain, belongs to the first element of the next chain of models. Oops, here it should be I plus 1. Here's
Wait, but M sub NP is not defined, is it?
M sub NP.
Right.
No, this is just yes. This P is a collection of good pairs, and I'm just saying that these are the good pairs
So
in the
those are
family.
conditions.
This is a single condition.
But you don't want curly brackets, I guess. This is ordered.
Yes, curly. Well, you
Oh,
can
it's a
put.
set. Oh, I see it's ordered by.
Yes,
this.
it's
Okay, yeah,
ordered,
yeah,
so it's
sure, okay, yes.
equivalent if I put one or
No, but
the
I was just asking, so, if I is equal to NP minus 1, there you get script M sub NP. Oh, but that's V, I guess.
Yes.
Oh.
Whenever something doesn't make sense, it's B. Yes.
Theological.
Yes.
Just to clarify, it's M minus of P.
Here? Yes, P.
P.
P, P. So I will, I think it's even larger to write this, but I will write this.
star mean?
Huh?
What does
That-
star mean?
Or it's
That
just
this
by
is
definition.
just the definition.
Yeah, yeah, sure.
It's just in that first model.
Yes.
But
Okay.
It just means it's in this, that means it's in the first index model, next in the next.
Yeah, so it's all
Exactly.
like the chain of chains really is it's chain.
Exactly. So it's
The first
So if
elements
you
form a
break-
chain,
break
the other
the-
ones are sort of dangling somewhere.
so yes, the picture looks like
Oh,
this.
yeah, you don't have the last ones. Wait. Hmm.
So the picture looks like this. If the n is 4, n plus 1 is 4, then the first good pair would look
No, but that's not what you.
like this. The second good pair would look like this.
Wait.
The third good pair would look like this.
But you don't have a, you shouldn't have a dot. I see, yes. So the yellow one is the M0.
Yes, the yellow one is the first model of each chain. Uh-huh.
And the red dot to the right of the yellow thing is actually associated to the previous.
Exactly.
Oh, yes, okay, yes,
So yes, each one is like associated to
okay.
this.
Yeah, all right.
Yeah, okay.
Uh-huh.
Okay.
It looks good.
Now, if you try to force with this thing, there's a, like we haven't put the wood property to destroy the n plus 1 entangledness, right? So the property is that the type of any of these two things is not the constant type. So 3 for any I and j less than np distinct. The type of AI, API, APJ is not constant. Mhm.
So you mean, that just means it's not
Oh.
increasing or decreasing.
Excellent.
Yeah.
So this is the force. As I said, like it's like not like the natural thing to do. That would be like just grab and press there, but like separate them using models. Of course, this is not a completely new idea, right? Even in the paper of Abraham, Rubin, and Shela, they sometimes use distinct models to separate pairs when doing some constructions. And yes, it's
Yeah, but they just have single models as usual, right? They don't have n tuples like this, as far as I remember.
there's like 1 or 2 constructions in which they use that. I don't remember the exact axioms,
Okay.
but of course it looks a little bit different because it's under CH and
Yeah,
everything
they
is.
just fix a chain.
But yes, the more or less the idea was that.
It's a long paper.
Yeah. I'm scared that they actually proved the theorem and it's so long that no one actually look at it.
Yep.
Yes. Okay, so this is the force. Well, there are things of the forcing which I think they are usual to prove, like when you have one condition and you add a big elementary submodel as a last part, you will always have a generic thing. Things like, okay, this forcing actually forces an uncountable set without any two things having the constant type. So the really non-trivial part is to prove that you preserve the n-entangled.
So yes, it's not constant, but is the place they're not constant vary? I mean, why couldn't you ask that they always be different on the first two?
Oh yes, no, it will vary.
Well, yeah,
It
so-
will vary.
So what requires you to make it vary?
To preserve the n-entangledness.
So
So
when you add a generic,
mhm.
what happens with, where is the non-constant?
In general, you will not know. The idea here is that whenever you want to preserve, this is destroying the n+1 entangledness of X, right? When you want to show that the n-entangledness of E is preserved, you will have together with each of these conditions an n tuple of E.
Oh, I see.
This n tuple is like distributed in these models in some way, and depending on where it's distributed, you will be able to destroy the increasing part on the remaining dots.
And I'm just wondering, in the generic, how do you decide, oh, I see, yeah, that depends on. Get the generic, guess you have to use, you know, the Albert argument with the trees and getting things. you know.
Exactly. Now, the thing here is that we will need to use like two kinds of arguments. Like we will use this argument with trees, but there are two arguments depending on the situation. So basically, the thing is that, as I said, one condition looks like this. When we want to prove that n-entangledness of E is preserved, each condition will have associated some points of E. Huh? Now, there are several things that can happen. I draw here many points. In our situation, here there are 4 points in each model, so we want to preserve the 3 entangledness of E, right? And this means that together with each condition, we take 3 points. There are some possibilities. Either each of those points that we take lies in one single chain, but each point in different models. And the other situation is that that doesn't happen. So there may be 2 points in the same model and another one.
That
in
exhausts the
the-
possibilities.
Yes. So the thing here is we will want to use these 3 arguments to reflect the possible changes of points here. But at the same time, since we want to preserve the n-entangledness, we also want to be able to reflect the blue points into lower models. The problem is that we cannot reflect 2 things at the same time. So we will have to prioritize which things we want to reflect. Either we want to reflect in some way the order of the blue points, or we want to reflect the order of the red points. And that is like the main part of the argument. So let me just put that with a definition. It's the following. Mm. So let M sorry. So let M be in SMK to the n+1 be a chain models, right? And let me call it B. In this case, not in xn, but in en. B in e to the n. Huh? We call B of the first kind over M if for each I less or equal than n, B intersection mi plus 1 minus mi, where the last point is the universe. This thing has cardinality 1. Second kind, if not. So yes, here we have this. Let me just draw the first kind and you can figure out the picture for the other one. If we have 3 models here, then something is of the first kind. If we have 2 points, in this case, which look each point in a donut, in a different donut.
Well, M has, they're N plus one, right? Shouldn't that be less than or equal to one? One of them might be M2, right?
Yes.
One of them. has-
Yes. Thanks, Paul. And here,
Mm.
I should also put less or equal than. Because this is like representing just one of these parts. I will take endpoints, but it might be the case
So
that,
It could be spread out.
yes.
Why don't you just say separated by M?
I don't know. If I was what said separated by n, someone would tell me, why don't you say of the first kind?
In the same vein, that little statement at the bottom that you're facing now, PFA for all Paul proportions if preserved that each graph in A. It should be a double
Yes.
statement.
Yeah. No, but yes, I just don't. I forget to speak in any possible language. So yes, figure out simple words. Okay, so maybe there's not enough time to give the complete argument because there are 3 of them. But let me put the theorems that will work and then decide what would be more convenient to prove. So we have these 3 lemmas. Lemma 1, which tells you the following. So let M A be a good pair. Just to remember that A is actually an element of X and not of E, let me instead call it X, right? So X is an n plus 1 tuple of X. I think it's a better,
So
Better.
GP is a good pair.
good pairs.
Or would-
Yeah, I didn't define it,
Better.
right? Yes.
Right.
Yes, it's a good pair and this is the set of all good pairs. So good. Let B be in En. B of the first kind. Of course, over M, and fix tau type. So if I have an element D in the first model, which also turns out to be a subset. This is for subsets of x to the n plus 1 times e to the n is such that xb is in D.
Hmm.
Mhm. Then I can reflect that thing in the following way. Then there is YA in D, but in the first model, mhm,
So, but if XB is in D,
uh-huh.
wouldn't that B then couldn't be of the first type because it's all a subset of zero, it's not separate.
Which one?
B, the B there,
Uh-huh.
Hmm.
B?
you have XB element of D,
Uh-huh.
and B is supposed to be of the first kind,
Yes.
but if XB is in M0, if B is in M0, it can't be separated from.
Yes, I should have
B-
said
B
in this, sorry, in the first kind, each thing is one, but in this picture, sorry, like the first element of B, it's outside M0. So I should say also the following thing. One, everything has cardinality M0, and two, B is intersection M0, B is empty. Does that solve your question? I should have said this.
Can you pull up the,
Huh? Ah, yes.
This seems to say that B might be a subset of M0.
No, 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 no. B is,
D is probably pretty
Oh,
large, right?
D is finite. D is not finite. D is gonna be some large.
no.
collection.
yes, so the idea is that,
Okay, fine. So it's gonna be, D will be in there, but B will not be, so you don't.
Yes.
Say that D is.
so the idea is that D will represent the possible candidates for elements of a subset. I,
Sorry, what you said, the B is still an element of M0.
yes,
Capital.
capital D is an element of,
No, it may not be, because D is large, not all of its elements.
yes.
Right, D is uncountable. It's not.
Oh, yes, yes, no,
But the usual
yes.
thing
Yes.
Useful thing,
Actually, the fact that that thing is in D makes D uncountable, right? Because B is,
Said in N, if D is an element of M0, all its elements are in M0.
No,
not
no,
necessarily.
No, but any element in M0 that's also in D
Yeah, so B
is
can,
not separate.
so by this B is
Uh-huh.
not in it. But so by this. So we know now that B is not in it. Because
That's
it is
what,
separate.
you'll take an element in M0 and D. Then it's also fails to satisfy that.
being of the first kind? Oh, yes, the thing is that we won't reflect the property of being of the first kind. What we will reflect is the type. Mhm. So this is the thing here. So let n be of the first kind. Then we can find this pair here such that two things happen. One is that the type of xy is constant. And two is that, let me put it in this way. The absolute value of the type of AB equals the absolute value of tau, which means that the thing here is that having certain type is not a symmetric relation, right? If the type of AB is the type of BA, but changing zeros by ones. So when I say that the absolute values are the same or the norms are the same, I just want to say that either the type of AB equals tau or the type of AB equals tau, but changing zeros by ones.
You should not say that absolute value of 0 is 1 or something like that.
Huh?
You're not saying the absolute value of 0 is 1. or
No,
the
no,
other way
no,
around.
no. It's a bad notation.
No, but it is 1 minus.
Eh?
Exactly.
One minus.
Yes,
So it's either tau or one.
yes. Maybe it's better to write it that way. Is tau or 1 minus tau. Yes? Okay, so this is the first lemma in case that the condition is of the first type. Now, in case that the condition, well, the point B is of the second kind, then we will be able to apply this lemma, but actually getting tau. Uh-huh. So the next lemma is let mx be a good pair, be in e to the n of the second kind, and disjoint from M0 and D as before. For each tau from n to, oh, no. Is not constant. For each
You
tau,
won't be able to add this,
Mhm.
right? This like, this is part of some extension of the condition.
exactly. So for each tau of from n to 2, there is ya in the intersection M0 such that what happens? One, the type of xy is not constant. And two, now you can assure that the type of AB equals huh? Right.
So- Dumb remark.
Uh-huh.
Can we just ignore the distinction between first and second kind and write lemma one?
One,
Can we
lemma
just,
one?
can we just write lemma one if we ignore the distinction
Oh,
between
yeah.
first and second kind?
How?
Well, just because the conclusion is just something
Right.
stronger if you have the second kind.
Uh-huh. Yes. Yes.
Does everything work
Yes.
using this lemma one
Yes.
where we erase lemma two?
Yes.
Okay.
Of course, lemma 2 is still important.
Wait, I thought that Spencer's question was basically just is lemma, I mean, it's proof that uses first or second kind, but lemma doesn't depend.
Yes,
on
lemma
first-
1 doesn't depend on first or second kind.
Right.
I'm writing it of the first, writing the hypothesis there of the first kind,
Uh-huh.
just to let you know that when we use it, we will use it for
Ah.
first kind of objects.
But you'll need this one as well.
This one only works for second kind.
But do you need, in the case where it's of the second kind, you need to know that you get actually tau rather than
Yes.
1 minus tau. You do.
Yes,
Oh,
and that is very important.
Uh-huh.
oh, okay.
Okay.
So maybe it's a good idea.
More fun stuff ahead.
Maybe it's a good idea if I, once that we have these two lemmas, I maybe can draw the picture of the forcing type of argument that we would do, and then prove one of those lemmas or prove what I draw then formally. Once that we have those two lemmas, the theorem is the following. P x E forces that E is n-entangled. And the proof goes as follows. So we take a name for a subset of E. Let names for names. Y prime be a name for a subset uncountable of E to the n of pairwise disjoint sets. Now we do the same as always. Take a big elementary submodel. So let n be an elementary submodel of a large enough structure such that the forcing and y prime is in n, and well, if you want kappa is in n, it's just necessary to say that, right? And the idea is that we can get a condition which has n intersection with h of kappa inside of it. And we can actually make it in such way that that intersection is the first element of a good pair. So there is P in P dx. Let's say R less than n sub P. Such that one n intersection with h kappa equals MPR0. And two, what? Yes, these P forces something inside the Y prime. So there is A. Did I call it A or B? B. B in e to the n such that B is outside NPR0. And P forces B to be in what? And here's where I stop writing and I start doing the draw. So this big line here represents MR0, which is the big model, right? After NR0, we have maybe some things here and some models inside. We have here, let's say, 4 points. Each of these 4 points, remember, each of these big lines represent the first element of a good chain. So here are the remaining elements. So what is the idea now? The idea is try to use this tree argument of Abraham Rudin al-Shelah to, okay, here we have these tuples of points and B, the element B in En, looks like this in the drawing, right? So the idea is now try to find the same picture, but inside the model. Let me put everything in white so that it's like a ghost that we want to find. So we want to find the same picture inside the previous model in such way that if we take the union of both conditions, that thing is again a condition, right? Now, these kind of arguments are somewhat long to write because it's like by reverse recursion. But the idea is the following. First, consider the first case in which first consider the second case in which all conditions look like this. That means if you look at this point B inside each of these red donuts, then that point or that set of points is of the second kind. That means there's less points than this thing, or 2 points are in the same block, for example. This would be a condition of the second kind. 2 points here and 1 here.
Oh, so is what you drew was of the first time.
No, the thing that I drew there is of the, yes, first kind, sorry.
So you want to consider the second.
Yes. So let's consider this thing of the second kind. Just maybe 4 points was small to really describe my problem with the argument. But the idea is the following. Let's say that I drew here 5 points and there are actually 2 points here and 2 points there and maybe 1 point here. So there are actually 5 points that don't count correctly. And the set B has actually 5 points in total.
Well,
Well, if they're 5 point, they should. have
There's
four.
6. There's the
Yeah.
white points are 6, sorry. The
So
white
4 is
points
6, 4 is 6, and,
and 5 is 5.
3 is
Exactly.
5.
So
Some chicken
Six to nine.
6 or 9.
first of all, since we are in the reals are second countable, each of these points, we can find a small enough open set inside the model, such that, well, that open set has each of those points and all of them are disjoint. And those open sets preserve the same order as the original points, right? Using that information, we can describe a set D. Like in this lemma, as the set of all pairs, such that the first element of the pair is the second coordinate of a condition, and the second element of the pair is something which is forced to be in a Y. Now, if the, let me now look this, and so using this, the second lemma in this case, we will be able to reflect 3 times. The first time we reflect, we have this type tau, which is not defined over n, but over a subset of E of size less than n. And so we have one original type tau here. Let's say that it's 0, 1, 0, 1, 1. This type here is associated to this tuple. We want to force a tuple inside, which has the same type, right? However, this tuple is separated in 3, which means that we need to separate this type in 3. So we can now use lemma 2, if we are in this case, to reflect first these 3 numbers inside here, this one number inside here, and this one number inside here. And when I say reflect, I mean preserving this 0 and these ones between the reflected points and the original ones.
So it's reflecting at the same time? Because usually one reflects one by one, starting from below, from above. And I'm
No,
not sure what
it's not reflecting at the same time. So I will reflect one by one. Yes, one by one, I will start reflecting until at the end, I use, well, like using that lemma 2, I will get a 6 tuple, which has like not constant type with this one, a 6 tuple, which has non-constant type with this one, and a 6 tuple, which has non-constant type with this one. This will make my condition an actual condition. Now,
Just the non-constant type one.
oh, yes, it's really just on, no, it's in all cases.
No, it's all,
Because-
it's for all pairs.
Yes, for all tuples here, the type should be non-constant.
Oh, for those two.
For non-tuples. No. Now, the thing here is that when I apply lemma 2, I will be applying lemma 2 not to my original type that I would take, but to these restricted types. So when the condition is of the second kind, that's why I actually want to keep all the types. So I can reflect all these things and non-zero will be changed to 1. Now, the other case is in which my condition actually looks like trapped inside a model. The real hard case is in which I just have these 3 points here. If I have these, 5 points inside those 6 points, then I can use lemma 1 repeatedly in this case in a trivial way, and in this case in a non-trivial way, to reflect these points inside here such that the type is not constant, and reflect the blue points inside here such that the absolute value of the types coincide as here. Well, such that this second condition happens.
I'm sorry, Mister, why repeatedly? You just don't just copy it once, but you're why repeatedly? You said repeatedly.
Because the first time I will have to copy these 3 points and these 4 points.
Uh-huh.
The second time, since I want my condition to be a condition, I need to keep doing that process.
Actually, you're finding a condition, you reflect one which has uncountably many extensions
Uh-huh.
with a property, and then you find one of those.
Yes,
Is it that, I assume that's what you're doing.
that is the argument. Mhm. And yes, that is what we need both those lemmas separately. And now the question is, why cannot? Uh-huh.
Types, I mean, if you reflect once and you're the positive version, another time the negative, then you put those together, that's neither positive or negative. And that's not how much times one way to step.
Exactly.
Oh,
That is the reason why I need to consider lemma 2. So I cannot apply lemma 1 if the 6 points that I take look like this, because here the type might change, here the type might change, and if it changes 2 times, then I'm screwed.
How does that help? Look, when you're doing the trivial reflection, you don't have to worry about that?
Huh?
No, but how does, in the case where all the blue ones are in one piece, how does that help with lemma 1? It seems you still have the same problem.
Because well, this is just a theorem of, well, not a theorem. If the type of, at the end of the day, I just want to find in the generic extension 2 points A and B, such that the type is tau, so I just get flicks.
If there's nothing there.
Yes.
then it-
Yeah, yeah.
Sorry.
Okay. So that is the basic idea. Now, one question is, why cannot I use lemma 2 always? I mean, why does lemma 2 needs the conditions to be of the second type? And the thing there is when we try to prove lemma 2, is like we're forgetting about this whole picture and just looking one single model. In this single model, this single chain of models, we will start reflecting each point once by like controlling the type or the order between the original point and the reflected point. However, I can just control at once either the order between the white one or the order between the blue one.
You said that before, but I don't see. I mean, you have second countability, so you can separate them by small open intervals and reflect. I don't see what goes wrong.
Yes. Let me.
It's really hard things to say.
So,
Oh,
Right, because you.
well,
right,
but
you
then
have-
with
you have to
different
preserve-
spaces.
so the thing is that, let's say that in the first step of that proof, I take this point and I find one point similar to that one,
Yep.
such that this point here is smaller than this one, right? So at this point, since I want the type not to be constant, I want in some way to change the order here. Now, the second step of the proof, when I build my tree, I want to take this point and this point and reflect them, right? If I consider this point here, and the thing is, I cannot talk about pairs of points. In my argument, I can talk about one point and say that there exists another in the reflection types of arguments. So if I reflect this point by saying that the order between this and this one is less, then I will have no control on what's the order between this and this reflection.
But I'm still confused. I mean, you can take arbitrarily small intervals,
Uh-huh.
and so just model knows that these points. So if you just take one which is small, I mean, you have different intervals and then you know what's the order.
Oh, but the
I
thing
hope
is that
this is something.
by this point, when you do that, is like you take these small intervals, right?
Yes,
The point that you find here will be inside these intervals.
yes.
And how do you know the order between those
Oh,
two?
between them. Ah,
Uh-huh.
ah, yeah, yeah.
Yeah, so you will know the order
Yeah, yeah,
between
yeah,
him
yeah.
and him. So that's the point. At each reflection part, I need to decide whether I prioritize the white one or the blue one. If the condition is of the first type and actually looks like this, in which all but one are blues, then I will need to prioritize the blue always because I need the type exactly to be tau, right? And there will be only one point in which I can prioritize the other thing.
But how would you get the one where one minus, because you have no control over the lights.
Oh, that's the thing. At one point, in which the white one is alone, I am able to control the white one. At the next step, I am always able to, I am also able to control the white one because the type is not determined by one single point. If I know that the value of a function at one point is 0, so yes, so let's say that the type that I want to put is this one between 2 points. It's the same whether I guarantee that I get this type or whether I guarantee that I get this other type, right? So the first time in which I reflect this white one that is alone. And the second time that I reflect, I can also reflect the white one to be of the other order so that I contradict the monotonicity, the increasingness, the constant function. At that point, when I reflect this point here,
Well, then you're done.
then I will be done with the white ones, but with the blue ones, I won't be done. The problem here is that since I didn't know how I reflected the blue one, here I might end up with a 0 or with a 1. But once I get the 0, 1, I know which decisions to make here, and I prioritize the blue ones.
So in fact, the failure of the card will always be at the top.
Yes.
So in fact, you can't, it's what I was asking before, it's, you know where it's going to be at the top element always, if you destroy the color.
No, well, no. What happens if
You can have more, yes.
yes, this is blue, then this is white, and then this is blue. Then in here, you would have to start with blue, then prioritize this one, then the other. So just that is more or less the idea. Sorry if I didn't have time to write it properly.
Very nice application of pigeonhole principle.
Okay.